Okay.
Second speaker in the Hagar First Street.
Great. Okay. Well, I sense from the size of the audience that a certain level of exhaustion is setting in, which maybe is not surprising. So, great. So what I want to do is, I think one of the main things I want to do is try to tie together at least two of the streams since we're sort of getting to the end of the week. So let me just recall from Cameron's lectures. The L-space conjecture. And that is for prime 3 manifolds with all of the other adjectives that Cameron listed. The following are equivalent. So first is that, let me maybe give the 3 manifold a name, Y. So Y is left orderable, that is the fundamental group of this manifold is left orderable. Second, Y has a co-orientable top foliation. And third, Y is not an L space. And as we know, this is it's known that 2 implies 3, and that's Azaf and Zabo plus others, as Rachel's been describing. Okay, so one thing that Cameron mentioned, and that I want to take as a point of departure, is that the L-space conjecture holds for Seifert fiber manifolds, but more generally, it holds for graph manifolds. And so that's 2 pieces of work there. So the first thing that was noticed and written down is that all of the machinery from Seifert fibered spaces can be pushed to the Seifert fibered pieces and made to work for graph manifolds. So the machinery relating left orderability and co-orientable top foliation. And this is work of Boyer and Clay, which now left the question, well, if I'm not an L space, is there a way to produce a co-orientable top foliation? And that's, in fact, the case. And I think, as Cameron mentioned, that's work of Hanselman, Rasmussen, 2 times, and myself. So this is where I want to pick up, like, how do you make something like this go? And I think the main idea, or the driving idea here, is to consider the set of all slopes script S sub m on dm when you have a manifold with torus boundary. Okay, so I'm adhering to Adams' convention, where Y will be closed manifolds, and M, for this talk, will have a torus boundary. Okay, so great. So what do? So what's the point? It doesn't make any sense to ask if M is an L space now. right, is the property of being an L space is about close to an L space. So what you do instead is you look at all the possible ways that M could give you an L space. Call this set M. So this is the set of all slopes, the boundary, such that M alpha is an L space. Okay? And I'll just remark for notation. So this is the Dane filling, or Dane surgery along alpha, and this set here, this you could identify with QP1. Okay, so this is all the extended reduced rationals that we're going to index these slopes by in the boundary. Okay, so you could try and study this set, and in fact that's what Rasmussen did. So maybe the first thing that you could observe here is that one of three things happens. So either LM is just empty. So maybe if you think that L spaces are rare, this is what you would expect to happen. In general, you know, no matter what slope I choose, I'm not going to get an L space. Another thing that happens is that this set can have exactly one element in it. So you could consider a knot in S3. S3 is an L space, but maybe that knot has no other L space fillings. Okay, so this is your typical knot in S3, maybe, with a complement of a knot in S3. And then finally, so far there's not a lot of content. Like, I mean, one of these three things is going to happen, but the content is really here. So, and in this case, and this is a connected interval. Okay, so realizing that this now is going to be some subset of the set of all slopes, you actually, it really does sort of divide into three very distinct cases. So a case that maybe we don't understand at all, a case that seems familiar from a typical knot in S3, and then the behavior that that we see in S3, where you get this sort of once you hit 2g minus 1, you continue out to infinity, you expect to see that for any manifold. So,
is it a closed interval?
Not necessarily. That, okay, which brings me to my, so the question was that is it a closed interval? And the answer is not necessarily, and I'll, so let me do an example. And so the example is to look at Sol rational homology spheres. Okay, so this also is going to pick up a thread in Cameron's lectures. So what I want you to consider is the following Hagar diagram. There's a genus 2 surface, and I'll try to emphasize that it's a genus 2 surface by putting a couple of compressing disks here. So there's beta 1 and beta 2. And I want to produce a manifold with boundary. So I'm going to put only a single alpha curve. Okay, so there's intersecting the betas in 4 points here. So what does this produce? This is almost, so this is a manifold with torus boundary without a border structure. So manifold that I'll call K with torus boundary. It's not bordered, so there's no border structure. But you could choose one, and you could try to compute from this diagram what the border Higgs floor homology is, and what is it? So manifold torus boundary, and it's got a name. It's the twisted I bundle over the Klein bottle. Okay, so I mean, this is not necessarily obvious, but this is a good exercise to work through, and it's an exercise related to one of Cameron's exercises about putting a ciphered fiber structure on RP3 connects on RP3. So the exercise is that to show that K is a ciphered fibered space. And in fact, it's ciphered fibered in two different ways. Okay, so that's something you can do by cut and paste. And then, you know, the hint is that you should start with this description of this manifold, and then along the way, convince yourself it actually has the structure of a twisted I bundle over a Klein bottle. Okay, so you know, maybe a more difficult exercise, if you are in the mood for punishment on a Friday, is to just pick a bordered structure and compute the bordered Higgs floor homology of this object. Okay. But there's two facts that are important here, and well, there's lots of facts. I mean, I think this is a really fun manifold. I say that because I spent a lot of time, and this manifold was under my skin. And I didn't think it was a very fun manifold, but then you grow, and I came to really like this manifold because it taught me a whole lot of things. So you should also suffer with this manifold. Okay, great. So here are the two facts. So first, K alpha. So if I Dane fill along anything, I get so pi 1 K alpha is finite unless alpha is lambda, the longitude, or the rational longitude. Okay, so in our notation, manifolds with finite fundamental group are L spaces, so that means that LK in this case is basically everything. It's all slopes except for one slope, lambda. So there's an example where it's an open interval term. Okay, and okay, so here you've got a manifold, all of whose fillings are L space. This is something that that Cameron alluded to actually. And then second, okay, because if you convince yourself this is ciphered fiber, then these fillings are going to have ciphered fibered structures, and this is something that had to be checked in these two cases when the base orbital fold is non-orientable. And then second, well, Y admits solid geometry. So this is a geometry that Cameron didn't mention, but it makes sense that he didn't mention it because so Y, if you're a rational homology sphere, admitting solid geometry, then you can write Y as 2 copies of K glued along some homeomorphism, where the longitudes are not glued to each other. Okay? So this is the sense in which solid geometry didn't show up. You know, if you believe this string of ideas and you work through the sort of exercises associated, you see that these are your sort of first basic examples of graph manifolds. Okay, so they have an interesting torus and they decompose into 2 ciphered fibered pieces. So where is this all headed? Well, you can prove, and we did, and I'm giving you sort of an anachronistic view of this on purpose, that, well, let's say it this way, Sol rational homology spheres are L spaces. And now from the, well, I didn't say the one thing that I was going to, the other thing I was going to say about this, but then, well, this follows from in one line, this now follows from the following, which is what I wanted to motivate and discuss. So now if you have these slopes, what you'd like is for an answer to this question to be strictly something that you can ask about information on the boundary. And that is indeed the case. So the main thing I wanted to talk about was work with Jonathan Hanselman and Dick Rasmussen. And that is that if you have MI that are not solid tori, and you glue these together, via some homeomorphism that runs backwards for convention reasons, then let's call this Y. Y is an L space if and only if when I take the set of L space slopes for M0, and I need to look at the interior of this set, and I take the union of that with take the image of the set M1, then the interior, then I should get all of the slopes in M0. So let me try and parse this for you. So this is, I think you can think of this as, why is it difficult to get an L space by gluing 2 3 manifolds together? Well, the condition I need to get an L space is that either I'm an L space slope in the interior of this set, and if I'm not, then I better be an L space slope in the interior of this set. So these 2 sets taken together have to cover everything. And so now notice that to get a Sol rational homology sphere here, you just need to check exactly the condition. So if this fails, if and only if you get this. Okay, so like as Adam said, calculating with domains is gross. So I think maybe I'm paraphrasing. You can do this directly, but it takes it's more than one line if you do it directly. But nevertheless, so there's where we're at, and that's where I wanted to kind of advertise this. Okay, great. I feel like I'm not quite woken up. It's going much slower than I planned, but okay.
So in particular, that means that both M0 and M1 must have intervals of space filling.
Precisely, yeah. So as I'm erasing that, that's exactly right. So a priori, a posteriori, you know that you need to already be working with something that has more than one L space filling if you're going to get any chance of getting an L. Okay. So
Taking that with the non-empty interior hypothesis, or not?
pardon?
I just wondered whether you were.
I just can't hear you.
Oh, if floor simplicity is your hypothesis in your statement, or if you're.
No, I'm sitting with Adam. I'm going to try and build up towards the general statement. But okay, so what Sarah's pointing to is that, you know, if you want to find I'm going to give you the nuts and bolts of the full proof here, but the what's available on the archive, there would be a hypothesis in this statement. Okay. Great. So maybe another thing to point out that what this does for you is, I mean, another example, but do I have time? Okay. So you could you could ask another question just about toroidal manifolds in general, and this allows you to say a lot. You can just start to construct examples. So maybe I won't say very much about this. But so if you suppose y is a toroidal rational homology sphere more generally, and let's let n be the size of the first homology, then and a few things happen. So if n is less than 5, or if n is 6, y is not an L space. And then you can just sort of keep moving along here, and you could ask, well, you know, when do I get a family of L spaces? When is that family of L spaces infinite? So when n is equal to 5, there's exactly, maybe I'll say equal to 5, respectively equal to 7. There's exactly 4, respectively 8 L spaces. In fact, all of these are gluings of trefoil exteriors. And then, so when do I get the first infinite family? At n equals 8. And indeed, this is now, how do you get this? You get it by gluing a trefoil exterior to a twisted eye bundle over a Klein bottle. So the twisted eye bundle over a Klein bottle will allow you to make infinite families. That's a neat thing to observe, or neat exercise. So as a corollary here, and again, this is picking up on both things that Cameron and Adam said, but I want to emphasize that if you know what's happening for graph manifolds, and you know this is telling you that actually you know what's happening for all manifolds emitting a geometric structure, except for those emitting hyperbolic structures, you're seeing here that they're really, what this is pointing to is that we're being asked to understand hyperbolic 3 manifolds in relation to Heegaard floor homology or their foliations and whatnot. So corollary here is that if y is an integer homology sphere, so a prime integer homology sphere L space with infinite pi 1, then y must be hyperbolic. or maybe it doesn't exist at all. I mean, if y is a, I should have said if there exists a y. Okay, you should annotate your notes. If such a y exists, then we know a priori it must be hyperbolic. So maybe just that I'll turn this into an exercise instead of doing it. But what would you do if you were trying to study this problem? Where you just start playing with examples and see what happens. So. And the first thing to do is to start with trefoil exteriors because they're staring right at you, because you just get your hands dirty. So let me fix M S3 minus a union, a neighborhood of the right-handed trefoil, and you write lambda and mu, and I'm going to write. Sort of funny, these are my basis elements. I'm going to describe the surgery plane in these terms. So this is 1 and infinity, and I did this. Yeah. And so here's your everything in this region here. This is your L of M, which is 1 through infinity, right? So this 1 is your twice the genus minus 1. And you could consider, for example, H that takes a boundary of M to a boundary of another copy of M. So I'll glue two of these together. Where, in terms of this basis, H is given by, okay, and study M union a second copy of M along H. And then you go back to this surgery plane picture and you ask, well, what could possibly happen? So you calculate so here's the line 1 for 1, and what you'll see so which order do they go in? We have 2 firsts, and actually what's going on here is that H of the meridian is 3 halves, and H of 1 is 2 halves. This is just multiplication by this matrix O. Acts on the right. So that I can multiply these vectors.
Why do you think it's going to be fruitful to try this one? Try this particular H?
Just start somewhere. I mean, I wanted to do something concrete rather than, I mean, I don't know. I'm certain you would have picked a different one. In fact, I'm certain everybody in the room would have picked a different one. I don't know a priori reason to think this is fruitful,
Great.
except that I've done the calculation. I mean, what I want to illustrate is, this is a really sort of a not that illustrative example because the sets were everything, right? So it's really easy to get failure. Here it becomes more and more difficult, and the reason is that, because I won't shade other things in, but this is, here is the image of so this is H of LM. Well, it's the complement. LM is sitting in this little wedge here. Okay, so the interior of the L space slopes of one plus the interior of the image of the L space slopes of the other are covering everything. Okay, so said another way, you know, the problem is start with one wedge that represents the L space slopes of one manifold, then what are the restrictions that, you know, what do I need to satisfy in order to get the complementary wedge of the other three manifold inside that wedge? And that's actually pretty stringent. And you see that, you know, once you've done an example, you see, oh, well, actually, this is going to be easier and easier the smaller the genus is, for instance. And then you apply a result of halogeny that says that, well, once your genus is one, and you want to minimize homology, and you know, you have to start with, the first time it's going to happen is with trefoil exteriors. And in fact, you need to get as big as 5 for that to happen. So this is maybe the exercise here, just to sort of check conventions, is that n equals 5 in this example. So when you start playing with this and you realize that, okay, well, I set my conventions up so that the size of the homology is sitting here, and then you know, modulo the minus signs, the numbers have to decrease as I go horizontally and across, and this is and the determinant has to be negative, et cetera, et cetera, et cetera. And there's so many constraints that you just can't, you don't start to see L spaces until your homology is big enough. And of course, this asks, you know, a more interesting question like, what's this sort of minimal n? What controls this minimal n as the number of essential tori increases? I think that's like a pretty question here. Okay, so the point is that this is a very stringent thing. This is a hard thing to satisfy. Yep.
H of 1 over 0, that's the vector 1 comma 0 multiplied by that on the left.
Yes.
So you get a minus, don't you get minus 3?
Oh, sorry. I got them backwards. Let's just do it. So I should get 1/2. Or did I 0? So that I just probably just totally blown all my conventions. This is fine. Yeah. 1, 1. So 1, 1 should go to no, you read this way, right? Infinity is 1 over 0. That's the point. Okay? So yeah, I mean, you have to read all of this so that the convention thing. But yeah, this is all backflipping so that it makes sense with the conventions I write down in a few minutes. But yeah, it's just, I don't know. You have every right to complain about these conventions, but they work. So 0 is 0 over 1, and infinity is 1 over 0. And so you read from right to left, and then it should be okay. So now if I multiply by 1, 1, I get 3 minus 2 as a denominator and 5 minus 2 as a numerator.
Oh, so that's H of 1 over 1.
Yeah.
So that means you're...
Oh, so that's the problem. So okay, there was a mistake. Great, fantastic. Thank you, Adam. So this is... There we go. That should be enough to sort it out. Fantastic. Thank you for checking my work. Okay. Did I say 2 over 2? I said 2. I meant, it's this one is, okay, so now, I mean, it's hard to know if the number of mistakes is decreasing, but. Okay, so now I think all the arithmetic mistakes are gone. So now we're back to wondering whether or not the conventions are correct. And I still feel like there's a chance my conventions are correct. Okay, great. So there you go. There's all right. So that's the point. It's not so easy to get L spaces. So what's the goal then? What I want to do is, because what this is suggesting, or what examples were suggesting, was the question of whether or not I get an L space upon gluing two manifolds with torus boundary. It appears to be just information about the boundary. So I'm handed this invariant called bordered floor homology. What I'd like to do is interpret bordered floor homology in terms of data in the torus boundary, whatever that might be. So let's talk about bordered floor homology now. Let's recall that A, algebra A, is described by a quiver with relations. And I'm adhering to Adams conventions here, so this is iota 0, this is iota 1. So I have two idempotents and three algebra Rabe chords. And I have to kill row 2 times row 1. And I have to kill row 3 times row 2. Okay? And we could draw pictures of these algebra elements. So if you think of a torus, where I've cut out the corners, and I've labeled those as 0, 1, 2, and 3. Well, I could describe this algebra in pictures, and it looks like row 1 is the directed path. It goes from the right-hand vertical side to the left-hand lower side. Row 2 runs up from the bottom to the left, and row 3 runs from the left to the top. Now I can start multiplying these. Multiplication of row 1 followed by row 2. If I allow myself to concatenate paths, it looks something like this. So there's row 1, 2. And here's row 2, 3. And then last, got a little bit eccentric. There's row 1, 2, 3.
How are you drawing the idempotents?
Yeah, that's great. That's the next thing I was going to tell you. So here's the idempotents in this representation, and then I'll explain how you could think about this if you wanted. So the idempotents, remember I've cut this open, so I'm going to draw 2 points, but it's actually 1 point. So the iota 0 is that constant path, and iota 1 is this constant path. And now I've said the word path, so how could you think about this little algebra as being sort of homotopy classes of paths? So the rule is that I've got two marked points, really. I've got a marked point here, and then I've got a sort of a secret marked point here, and it's homotopy classes of maps from the interval into this torus, where the endpoints sit on either one of two base points, and they have the rule that they have to always hold this funny marked point to their right, and they can never have this star to their left. Okay, and then if you think about that for a minute, that means that there's now a unique constant path, because you can't leave and come back, because somehow this second base point is telling you to flow. Okay, but and now multiplication really is by concatenation, and I concatenated, for instance, row 1 by row 2, and that's homotopic to row 1, 2 through holding this point on my right. Okay, well, I don't really want to add extra base points, and it's sort of saying way more than I need to. It's such a small algebra, and we have a great description of it. But this gives you in pictures what's going on, and it kind of gives some geometric meaning to the idempotents. In fact, the idempotents are just, you have two different base points, and they're sitting on each of the two alpha curves, if you want. Because that's what I get when I have a bordered manifold. I have a puncture, and then I have a collection of alphas.
Can you do that for a higher genus surface?
I I don't know. I don't think so. I mean, I don't know what the. Well, I haven't thought about it. But there's a differential there that I don't know how I'm going to take care of in this cute way. Okay, so I think you should just take this as cute until the next thing I say, which is this is now going to give me a recipe for taking description of the border invariants and realizing them as an object in the boundary. So you should imagine this is the boundary of your bordered drew manifold. Okay. And the two arcs that I've cut along, those are exactly my two alpha arcs. Okay. So now, let's do an example that will probably stick with us for most of the rest of the time. And that comes from Adam's lecture. So M will again be S3 minus the right-hand trefoil. And let's recall, based on the recipe, Adam gave us what the invariant looks like. Okay, so I'm going to decorate my idempotents. These are now I have a vector space over Z mod 2Z of dimension 7. And the vector space is split according to an idempotent action. So the coloring means which idempotent. That's the same as the idempotent information here. And so that this doesn't get confused with path algebra, I'll shortcut things and I'll label edges based on their algebra element rather than writing row. Okay, so there's the bordered invariant. What is this bordered invariant? This is CFD of M. And if I'm being careful, it's relative to the zero framing. So this is relative to the bordered structure that's determined by the longitude and the standard knot meridian. Okay. Okay, so that's a bordered drew manifold, and that's exactly the recipe that Adam gave us, with the understanding that I'm just writing subscript. So if I just won't decorate an arrow, or I'll put empty set when it's an internal differential. So in fact, this is an example of a reduced type D structure because I don't see any internal differentials, and you can always get one of those by canceling those internal differentials, up to getting something perhaps more complicated. Okay, so now I want to imagine what this is doing in the boundary. So got some marked point. Put a second little box here. And now in red, I'm going to draw a curve that is highly motivated by the labels I see on these edges. So for instance, there's a row 3, which would pass to the other side and pick up a row 2. So now pass to the other side of my torus and pick up a row 1. I'm here now. Then I should run backwards along a row 2, 3. Move to the other side. Where was I? Now there's another 3. Followed by 1, 2, 3. And finally, and backwards 1 to 1. Okay, and the vertical intersection points with these horizontal lines, which aren't doing anything except for running horizontally outside of this box where all the action is, are my intersection, are exactly the dimension of my iota 0 summand, and then my iota 1 summand is the intersection with the horizontal. Okay, so if you like my conventions here, what have I done? I've cut open along lambda and mu, which will explain begins to explain the backflipping I was doing for this example of convention. Okay? Okay, so what have I done here? Well, nothing. I've just taken this graph and I've implanted it in the torus boundary according to this set of rules that was given to me by the homotopy parents. Okay, so do that for a second. Okay, so I haven't said much. I've tried to be suggestive, but so maybe I should ask: are there questions about what that recipe is? Okay. So it seems a little naive, but as a starting point, here's why I think it's not very naive to do this. So this is, again, was an observation of the Rasmussen team. And that is that if you're in this case where you have more than one L space filling, then CFD M, say lambda mu, pick some basis so that you can compute this thing, may be represented by a valence 2 graph. Okay, so why did this trick work? Why did I get something that looked like an immersed curve? Well, it worked because the graph was valence 2 and I get a curve component for every time I pass around this curve. So this is something that is called loop type. Okay, so maybe, pardon me. Here's some exercises. So in the case of S1 times D2, okay, so there's a perfectly good manifold with torus boundary, and you could attempt to compute the invariant, and since you've been thinking about bordered, you should try and convince yourself that that is going to be this curve here. Okay, ignoring orientation. Second, you could look at the manifold K, and so I've said that the graph is valence 2, but it need not be a connected graph. So in this case, you see that. Okay, and I should say so this is a cruel exercise unless you do the other harder exercise, which is calculate the thing to begin with. So let me tell you what the answer is here. So if you want to see where this comes from, you should look at a paper by Steve Boyer, Cameron, and myself. So you can explicitly compute this and then use this recipe to see that at the homotopy you'll get this picture. And then, yep.
And then that has only things on the vertical basis.
Yeah, so I've done a little homotopy and I'll say that, so this is at the homotopy. Which is the next thing I was going to write, but so, but I didn't really want to say so. Okay, we'll write that in a second, but you're absolutely right, Adam, that this is not quite yet sensible as written. So here's the way to convince yourself that this is the right object is that when you take the figure 8, the curve, the invariant here is the figure 8. So this is what you get when you take. And this is going to use the recipe that Adam was describing for how you get the bordered invariant for a knot complement in S3 and then translate it using this recipe. Okay, so maybe, but the harder exercise is to convince yourself that star holds in S3, and that's where this result here. Okay, so Adam told you how to go from the knot floor homology to the bordered invariance, and he also told you what the knot floor homology of an L-space knot looks like. And so that's a trickier exercise. Is you're not going to write one description, but you can get a feel for what the description looks like. Okay.
So what does K look like before you use that homotopy? Because right, I would want to see this 6 generator. Right now I see 4 generators, and well, I have 2 of them gone away. Or how do you bring it back?
I mean, 2 of
For K, shouldn't you have 2 generators in the other idempotent?
yeah. So I'm gonna have to. Okay. Do you want me to do the exercise? What is it?
No.
I mean,
Oh, I see. Okay.
okay. You should cut and then move part of. You should cut just above that star and move that part of the square down. That's just like sort of sliding your picture up in the torus, and you'll see them. The corners now dip around the edge, and you'll pick up pieces of the vertical idempotent. I think I should be able to happen. Unless yeah.
What is the meaning of that star?
That's the base point. Thank you.
But it's the Z base point of the figure floor homology, or it's a different base point?
Yes, it's exactly, yeah. So the answer to Paolo's question is which is required
particular oromorphic disks are not allowed to cross.
correct. But there are no disks here yet. This is, yeah, okay. Exactly. That's the reason that in this picture, why you don't see a curve that's passing over with this star to the left. If you go back to this rule. Okay. So, well, Adam, you got me worried. Okay, I'm not going to do the exercise after and decide if I'm writing that scribble. But the theorem here, and the reason I'm attempting to be flippant, is that this curve, this immersed curve, and the M, so that's call this lambda m, perhaps ignoring arrows. Well, first it determines, and it's determined by CFD of m and the mu. So it should say this inverse curve when it exists. That is to say, in this loop type setting, when I can write this description, it tells me everything I need to know about the border invariance, and it's completely determined by the border invariance. It's not, and indeed, I need to know the border invariance to write it down. I'm not telling you that I have some other way to get my hands on this curve. It's a graphical description. But what's interesting is that it doesn't actually depend on this this framing. So as an abstract curve, is invariant of the homotopy and does not depend on this choice you had to make to define CFD, in particular lambda mu here. So where is lambda mu showing up? This is an artifact of the fact that I wanted to draw this curve in the torus with a mark point. I wanted to draw it on a square for you, so I had to cut along two lines, and those two lines were the spaces. And so what I'm claiming here is that if I cut along two different lines, say lambda and mu plus lambda, well, then I'm going to get an a priori different CFD, and indeed this picture will look different. And I can work out exactly what those are using the bimodules for Dane twists. And of course, we didn't write those down explicitly, so we won't go through that explicitly, but you can look at exactly how this is going to change by looking at the action of the bimodules. The claim here is that change is exactly compensated for by the plane shear that you would do to change your description of the torus. Okay? So this really is, it's just that what happens when you go from thinking about an abstract surface to, the generic embedding of a surface. You start making choices, and things appear to have properties that, that aren't really a property of the intrinsic curve itself. Okay. Great. So somehow you could wonder, like, well, why is all this information being held by just a curve, and start to hope that in fact the whole theory of bordered floor homology for manifolds of torus boundary is just a story about immersed curves in the torus boundary. Okay.
So if part of your curve is just contractible, can you just remove it?
Yes.
Is that what's happening in this example 2, exercise 2? Or not? No.
No.
Okay.
That's not what's happening there.
But the reason there's no vertical thing is because it's homotope. So.
Am I worried about
What?
I think I have to tell you one more thing before that picture makes any sense. That's what's happening. That's what's going on. So exercise 2 should be in quotes, and you're supposed to extract the correct exercise from the next half hour of the lecture. This is, I was trying to squeeze too much in. Now I'm just accepting the fact that it's, we're going to just have to talk during the break. But, I was trying to tell, yeah, okay. Well, there we go. Okay, so now, so far, what I'm trying to emphasize, the way I'm trying to tell this story is that this is an extremely naive thing to do. And now I want to convince you that that more of the information is packed into this picture. So now I want to talk about pairing. So, and the way I want to motivate that is that Adam gave you a description for what pairing is in terms of the box tensor product. And I want to try and interpret that graphically so that you at least have a choice. You can decide, well, either you'll say, well, that's a much better way to think about the box tensor product, so I'm going to stop thinking about the box tensor product, or I'm going to convince you that really that box tensor product was not so bad after all. Yeah.
Before you, can you just clarify something you said before? When you're talking about the different ways to cut,
Uh-huh.
is that what you're saying that you have the action of the mapping class group by modules, and you have the action of the mapping class group on merged curves,
Yes.
and those actions are compatible.
Yes. That's what I'm saying. So I'm saying. So let me paraphrase Tony another way. That if you now want to go and reverse engineer what the action of the Dane twist, the meridional Dane twist is, for instance, then I should cut this torus on an angle, and I should rearrange the pieces to get a new torus picture that'll look like a lozenge with different sides identified, and that's going to pull this curve all over the place. It's going to look different. And in fact, the way that it looks different is exactly what would happen if I hit this with the meridional Dane twist, which, as Adam said, is going to fix those horizontal and vertical edges, and it's going to lengthen, or actually shorten the edge that runs on the diagonal. So yeah, those two actions are compatible. You can use it to reverse engineer by module. Okay, so now let me take some time to explain pairing as a way to motivate this. And I want to reuse this picture here.
I see. Oh, because if you, just to see it, if you stretch that picture horizontally a little bit, there's one vertical line that meets the red in exactly one point. And if you were to do a vertical Dane twist there,
Yeah.
you'd be inserting a row 2, 3 is
Exactly.
supposed to correspond to a horizontal segment, and you'd just be adding another one of those.
Yeah. But then you just figure out the conventions. That's actually going to be the negative Dane twist. So that compensates exactly for the
Yeah,
balance.
that's adding it.
Okay.
You got it. Okay, cool.
Leave this. Okay, so here's what I want to do. I want to put another box here and consider maybe a simpler curve, which I'll draw in blue. Okay. Okay. And now, away from this base point, you see certain bigons. Okay. So here's a bigon, for example. And so I'll use the same marking scheme. I'm going to claim that the item has been flipped here. And the intersection points that I'm writing down here are these 3 vertical dots from the horizontal with the closed idempotent, and then the open idempotent, these 4 horizontal dots. And I've arranged them in the same order because I want to reverse engineer the box tensor product here. Okay. So this bigon is going to hold. This is a map from here to here, and that's coming from. Just cancel out this pair. And that bigon, and there's a second bigon. Let me get rid of this bigon. The second bigon is everything you see here. And it finishes here. And it runs along this direction as well. Okay, so I see these. And those are all the bigons in the picture. Keep track of the second one by a map here. Okay. Now I want to hold that picture in in the background for a second, and then go back and explain what would happen if I were to box tensor product the two curves corresponding to these red and blue curves together. Okay? So each of these I claim are representing different bordered invariants, but there are some funny conventions because I've taken the bordered invariant of the torus, so spit out this curve into its boundary. The bordered invariant of, well, this more simple curve, you maybe are not, won't be surprised that it is just a solid torus. I'm doing some Dane filling, but I want to compare the two curve invariants in the same torus, so I've had to map one over to the other. And as you know, the box tensor product, that I need to have type A on one side and type D on the other side. So now, I started with a graph and I built a curve, but I was very agnostic as to whether or not this was a type D curve or a type A curve. So actually, it's neither. And the curve, there's a recipe for extracting a type A structure from the curve or a type D structure from the curve, and this is reflecting the duality that I was talking about. Okay, so the first thing I'm going to do is I'm going to consider the torus, the trefoil as a type A structure. And if you go through the rule that Matt and Adam write down is that you need to flip all the 3s and the 1s and then interpret differently. So here, okay, so now I'm going to perform Adam and Matt's algorithm, and I'm going to write brackets around things so that, mainly so that I remember that I've changed them, but also I want to be able to interpret this graph as having an A infinity module structure. Okay, so then there's now these last two things, something funny happens. So this 1, 2, 3 changes to a string 3, 2, 1. But of course, on the type D side, 3 times 2 times 1 is trivial, but this is actually a higher multiplication. So I keep track of this string as an M4, 3, comma 2, comma 1. Okay? And similarly here, there's the 2, 3 turns into a 2, 1, which I parse as 2, comma 1. Okay, so this is all using Matt Hedden and Adam Levine's interpretation of what happens to a type D structure, a reduced type D structure when you apply the AA identity bimodule. Okay, so that's like maybe a tricky exercise to go back and understand that bimodule and see where this proof comes from. But it's written down really nicely in their paper. Okay, so there's some other information you have to keep track of now. Maybe I'll do that in another color just so that it's easier to look at these things. So there's some extra arrows here, and those are because there's higher multiplications, and the higher multiplications are of the form. And this is a 2, 3, and this is a 1, 2, 3, and here this is a 1, 2, 1. Okay, so the point is you have a graphical description of these A infinity modules. It's just that the graphical description is a little bit more nasty because there's more operations. Okay? And then I want to box tensor that with a simpler object, just this, type D structure that has one arrow labeled 1, 2, 3 and the other arrow labeled 2. Okay, and this is, so you'll see that it's not quite this curve, and let me explain what we did after we sort of go through this more ad hoc description of what's happening. Okay, so where do these two edges come from now? So this is in green, so this comes from the fact that there's a M2 that takes in a row 2, and there's a D1 that spits out 2. Okay, and those pair up in the recipe of the box tensor product to give me exactly this arrow. And the mnemonic I'm using here is I see that when I form the chain complex, I've got exactly one closed dot and one open dot. So the number of generators I have is going to be exactly 7 again. I'll pick up exactly one closed dot for each closed dot and one open dot for each open dot. So that's why I have this size of chain complex. Now I'm going to go looking for which operations match up. And then what I want to pick out on the picture here is that there are two corners picked up by these little boxes here. So these boxes, I want to call this the A box. Call this the D box. Okay, and these corners now have rules, and the corners are that this corner, when the blue curve passed through this D box, it picked up a 2, and when the red curve passed through this A box, it picked up a bracket 2, and those two algebra elements match up exactly to give you a differential in the box tensor product complex. Okay, so this is why I'm identifying this specific bygone with this particular specific operation here. Questions? So I mean, okay, it's still, as Adam likes to say, black magic. But let's pick another color and single out this 1, 2, 3, because I do see that I have a 1, 2, 3 here. In fact, those are the only things that are going to pair up. Yes, this is unbounded, but on the other hand, this is bounded. And there's the higher deltas that this will spit out are things of the form 2, 1, 2, 3, etc., or 1, 2, 3, 2, etc., and I just don't see any strings like that over here. Okay, so I am only going to see 2 arrows, and these are them. And then I want to match this up with the other bygone. Okay, and hopefully use this to describe better what's going on. Okay, so what am I doing here? What I want is to take the pair of immersed curves in the torus boundary and then do exactly what Adam was doing with simple closed curves to form the Heegaard floor homology for a genus 1 splitting, but now I want to do the same thing but with this set of immersed curves. And what I'm claiming, or slowly trying to illustrate, is that when I put the curves in this particularly nice form that was given to me by the graph I started with, that the box tensor product comes along for the ride in terms of particular bygones that measure particular operations. Okay. So now let me tell you the rules that. So here. We're actually doing, well, we just identified it. This is -1 surgery. On the right-handed trefoil. Well, the curve that I'm filling with is either +1 or -1 as a slope, modulo your conventions, and then I'm seeing that the size of the homology this is spitting out is too big to be at L space, so it must be the -1 surgery. And having said that, this is supposed to make you wonder a little bit about the conventions, like what's going on. So type A conventions here. So as promised, there's 2 ways to read off what's going on. So the type A, if I look in this type A box, well, the way I'm claiming we should read off information is by looking at a given bygone and then reading off how that bygone intersects, this immersed bygone, how it intersects the A box and how it intersects the D box. So this is what I want to encode as 3, 2, and 1. Okay, so I'm claiming that when I interpret this graph as a type A module, then I can embed it into the torus boundary and read off these corners as telling me 3, 2, and 1. And then on the type D side, there's a funny reflection that happens to make this compatible with ordered. This is one. This is the reflection that gets me every time. Actually, I'll admit, I was up a little late last night trying to remember why we picked the conventions that we did. But these are the conventions that are written down, so I'm going to stick with them rather than 11:30 last night seemed like a bad time to overhaul our conventions. So I didn't do that. And then what am I going to do to tell you about how I'm reading off this bygone? I want to pass to the, so consider the cover of the plane minus the lattice points. So this is of dm minus this base point, this special mark point, and let me do it here so I have lots of space. Great. So if I pass this cover, I need my colors again. That's what I'll see as the invariant for the trefoil. That's the curve for the trefoil. Up to wiggling it around a little bit. And lifting the other curve then becomes something like okay. And for instance, here's the bygone, the green bygone. Mark 2, 2. That's this bygone sitting right here. It canceled out. It's like that bygone is telling me that I can pull those curves apart and get rid of those intersection points. And now, this is giving you a better picture for how to understand what the different Dane twists do. Let me just focus on these 3 tiles in the lift. And now I realize that this, because you guys are taking such careful notes, this should have left. No, that's okay. Okay. So there I go. I've got 3 tiles, and the bygone that I'm concentrating on is this one. So what I'm claiming in this picture in the lift, all of these bygones are going to break up into simple building blocks. And the simple building blocks here are, if I go back to my conventions, the blue, this is a 1, 2, 3 corner. 1, 2, 3 type D corner. And then the other corners, as they pass through this other box here, and okay. This is the A box every single time. Well, what do I pick up? I pick up a 1, and then a 2, and a 3, which by the conventions of how the type A to D or D to A conversion goes, that these should be multiplied together to give me a row 1, 2, 3. So these are spitting out 1, 2. So this type D structure spits out a 1, 2, 3, and this multiplication takes in that 1, 2, 3. And that's how you see the decomposition in terms of the bygone. Okay. So why am I telling you this? The claim is actually that that this recipe keeps working. That in fact this recovers the box tensor product for what? So I've got M minus the trefoil, and to that I'm mapping D2 times S1, and here I'm taking the boundary of D2 times a point, namely the meridian, and H is mapping that to lambda minus mu, namely minus 1 surgery. Okay? So, what is the theorem then? Let's go back to our notation. So I'll suppose y is m0 union m1 along some homeomorphism, where in particular h takes the boundary of m1 to the boundary of m2, m0, and it's carrying the base point z1 to the base point z0. And then for the moment, let's suppose further that mi are loop type. What does that mean? I.e., the gamma mi exist, and from that, let's set gamma 0. So this is going to be my red curve, like. That should just be gamma of m0. Red curve, I'll interpret that as the A-type curve. And I have a blue curve, or a collection of blue curves, with gamma 1. Now this is where you start to see the artifact of some of the funny conventions. I call it H bar, gamma of m1. So this is, I want to compose H with the involution that takes mu inverse and lambda to lambda inverse. And this I have no explanation for. So this is a symmetry that is satisfied by all the three manifolds that I know about, but I don't have a proof that this symmetry is satisfied. So you shouldn't really need this bar, but currently you need this bar. And that's reflected in why the 2 moved up to that corner, actually, really, in the convention. But I don't have, okay. So that's the deal of how you compare these two. So what's the point here? I'm trying to compare both of these curves back in the boundary of m0 minus its point, and then I want to compute the intersection floor homology of those things. So that's the theorem. HF hat of y is the floor homology of these sets of immersed Lagrangians, gamma 0 and gamma 1. So the immersed Lagrangian intersection homology computed in dm0 minus its base point, z0. Okay? And this is the main reason for doing all of this yoga. And this is written down in a paper with Jonathan and Jake. Okay, so just to step back, what have we done? We've found a recipe for interpreting the bordered invariance as a particular flavor of curves, and then we've I'll just finish and then I'll get and then by judiciously choosing the recipe for those curves, we've made it so that the count of bigons gives me exactly the counts that I would get from the box tensor product. And then I observed that those bigon counts, because the curves are nice, they're unobstructed in particular, I'm just computing immersed intersectional Lagrangian floor homology in this torus minus the point.
Yeah, I was about to ask why they're unobstructed.
Yeah, so they're unobstructed because of my recipe. So as we went through the recipe, the way it's built, you never get fishtails. There's another way to see this in terms of there's a mod 2 grading on the on border that neither Adam or I talked about, and from that grading, I can write down a word in open dot and closed dot as an element of the free group, and this gives me a homotopy class in the punctured torus, and it's homotopy through the immersions never show up, and you can't create them through this regular homotopy. So, I mean, we just impose that in our recipe, and you don't see them. Maybe maybe a better, more concise way to say that is I don't need immersions to describe the border invariant. Okay, that's a really good question. Okay, so I think to bring this back to what Adam was talking about, I think a good thing to think about is what is this really generalizing from the standpoint of things that we've already seen. And so the first remark from Adam's lectures is that well, Adam computed HF hat of L, let's just do an example, L31, say. This is, as he described it, I'll just do this in pictures, the floor homology for now embedded curves of, well, I take the genus 1 splitting for my lens space, and I mark a point and put that point on the boundary, and so in the case where you admit a genus 1 decomposition, that's where you can define the Heegaard floor homology on the torus. And so we're generalizing, instead of generalizing the direction of increasing the genus of the splitting, we're saying, you know, if you have a torus at all, then you should try and cuddle on that torus, encode the information of the two pieces of the 3-manifold in terms of data on the boundary, now in terms of a more complicated curve that I can't see where it comes from precisely. I mean, I know it comes from border, but I don't know where it comes from. If it comes from someone more natural, and then I compute the floor homology to see the box tensor product, and that's a direct generalization, if you like, of what was already happening for Heegaard floor homology. Okay? And then the second remark, and this is where I'm going to start trying to save myself some time, I think. So as a special case of this. Of the L-space Goulding theorem, well, you could imagine something like this. So I've got this marked point, and I look at this marked point, you know, in some small radius epsilon. Okay, and my curves are allowed to homotop wherever I like, but they're not allowed to pass over the curve. So I could put, instead of putting the point there, I could put a little peg there, and so you'll see things like this happen. And I expect the curve to pull tight against the peg, and you could consider slopes tangent to a peg, say, and take maybe a little band that's twice the width of that epsilon centered at that curve, and find another curve right here. And actually, by doing that, what you're observing is that, you know, tangents to the curve correspond to places where I have a bigone that covers the base point. Actually, what that does is it produces two generators that are in the same spin C structure. So tangents to the curve end up producing L space knots, non-L spaces, and then I minimize over epsilon. And then going the other way, if I find such a bygone, so I find two generators that are in the same spin C structure, so I'm non-L space, well, then I use the mean value theorem and find a slope. Okay? So what are you really doing here? If you want to determine the L space slopes, well, you go back to this picture, for instance, so e.g. So there's my trefoil curve. And now in green, I'll write what happens if I pull tight against pegs of epsilon, radius epsilon, and then I make epsilon very, very small. What'll happen is I'll get some zigzag pattern like this, right? So I get some kind of singular curve that hooks up on all of these base points. And the point is that this little, remember that my conventions for the sake of drawing were that this was lambda and this was mu, i.e. this was 0 and this was infinity. And then you look at this wedge here. And the interior of that is all places where I don't have a tangent to the curve. So this wedge, this is L sub S3 minus the trefoil, which is, as we know, is set 1 to infinity. And this point of view is nice in the sense that you see that there's in terms of tangents to the curve, there's some funny behavior at the two boundary points. And this is, if you go back and unwind, this is related to the fact that we have to pick the interiors when we get an L space gluing. Okay.
Even that I'm not understanding what's going on. Your picture with the zigzag is somewhat evocative because the segment of the zigzag should correspond to sutured homologies. Is there any way to make sense of this observation?
No. I mean, what a great question. I would like to make sense of that question, but I can't. I don't have an answer. Maybe Jake does.
So, I mean, each of those segments of the zigzag corresponds to the sutured floor homology where you've taken a pair of sutures whose slope is at a boundary. Well, in this picture, they're both at the boundaries of the L space intervals. I mean, in general, they might not be at the boundary of the L space interval.
Do you want to answer his question after?
Yeah.
I mean, what a good question. Okay, so I have 25 minutes, and I want to try and convince you that this is a reasonable way of thinking about things, even if it seems very specialized to restrict to this loop type setting. Okay. So I think what I should do is just pick a running example and try to do a cartoon sketch of what's going on here. Here's the running example. So I just cook up a type D structure essentially out of nowhere. Now this isn't out of nowhere. It's from like every other page in my notebook because this type D structure has been bothering me for some time now. But as with the twisted eye bundle over the Klein bottle, I have come to like this example. So I want to use the same recipe. I want to now just try to naively construct an object in the torus. And that's what the first thing I'm going to do. So here's the naive object. Let's say naive geometric realization of this graph. Same deal. I'm going to try and have it so that all of the information, all of the complicated information is packed into the corner here. So okay. So there's everything but that arrow that's crossing over. So everything in red is that loop and that loop. Okay. But then, let's say if I switch to green, I could also add another one. I want one that's going from this loop to this loop. So that should be that guy here. So the naive object that captures the same information as that graph, in fact, it just puts that graph into the torus boundary, is this train track. And because it's kind of close to t and it has a nice immersion in it, I'll call that var theta m. Of course, this assumes m exists, but I don't have a three-manifold that corresponds to this. That's not the point at all of what I'm saying. Okay? In fact, let me say how much that's not the point. I don't have any example of a three-manifold that I know is can't be described as a valence 2 graph. That's just one of the shortcomings that I'm dealing with in my life. Okay, but there you go. So we have a train track, and now we have to think about whether we can manipulate train tracks. So just as naive objects, as long as you're careful about, and you don't worry about whether it's an invariant of like whatever these objects are in terms of the torus, you can now do the same naive game, and as long as you take bygons that are carried by the train track, you'll just recover the box tensor product. Okay, so you can get a picture of what the box tensor product is doing here. Paolo, go ahead.
Yeah, the red arrows don't match.
Which red arrows don't match?
While the two pieces don't move to an oriented curve.
No, they absolutely, they're not an oriented curve. The way I got an oriented curve before was I just forgot the arrows. I mean, I wasn't oriented, okay? But now I'm going to explain why that was a reasonable thing to do right now, okay? That's a great point. So this is, really you should think of this object, and in fact the object I had before, as just some recipe that takes the abstract graph describing the type D structure and places it on the torus in such a way that it picks up the corners exactly the way it should pick up the algebra element. Okay? Great. So, okay, so now there's an extended algebra. So I want to take an algebra very closely related to this algebra. Remember I had row 1, row 2, and row 3. And I'm going to add one more edge called row 0. And then I'm going to quotient by row. If I multiply these in the wrong order, modulo 4, I'll get 0. So row 1, row 0 doesn't make any sense. Row 2, row 1 doesn't make any sense, and so forth. And I want, at most, one row 0 occurring. Okay, so I'm going to kill any sequence of row 1, 2. So if I have row 1, row 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, I'm killing that. Okay, so I can have any strings of 1, 2, 3, 0 that have at most 1, 0 occurring in the subscript. Okay,
And that's a cyclic order.
and it's a cyclical order. Thanks. Okay. So what am I doing here in terms of that picture? Now I'm allowing the same curves, the same homotopy classes of paths that have endpoints on the boundary, but I'm allowed to cover. I'm now allowed to cover the star to my left at most once. Okay, so I'm going to pick up a little bit of the U map now, and in fact. Okay. So, okay, so instead of F, now I'm going to work over F modulo F adjoin U modulo U squared. Where U is acting by row 0, 1, 2, 3, plus row 1, 2, 3, 0, plus row 2, 3, 0, 1, plus row 3, 0, 1, 2. Okay? Great. Okay, so
Does that mean row 3, row 0 is not 0?
row 3,
Oh, sorry, row 0, row 3. Never mind. Got it.
Yeah, exactly. Thanks. Right. This is, you're asking Adam's question here, which is exactly the right question. It's important that this is the cyclic order. Okay. So here's a proposition that's extractable from Lipschitz, Osvath, and Thurston, and that is that if you have any CFD so if you, what is the statement here? If you do come from a three manifold, so I'm not saying anything about these graphs in general, but these train tracks in general, but if you do come from a three manifold and you have a type D structure associated, then this object emits an extension over this extended algebra such that, so formerly d squared was 0, but now this new d twiddle squared is u times the identity. Okay, so the differential now squares to u rather than squaring to 0. Okay, so that tells you something. So for instance, so now to answer Paolo's question, or partially, so why can you forget the arrows when you're in this loop type setting? So if I'm, for instance, if I start with x and y, so two generators, and I take the type D structure that has one arrow labeled 1 and one arrow labeled 3, well, here I see that, for instance, d squared of x is 0, right? So this is, if I square x, I get, or if I take d of x, I get row 1, 2 plus, row 1 plus row 3 times y, but then d of y is 0. But on the other hand, what this is saying is that I should get, again, for idempotent reasons, d squared of x, d twiddle squared of x should be row 1, 2, 3, 0 plus row 3, 0, 1, 2 times x. The reason you're not seeing all four elements is two of them are acting trivially because of the idempotent of x. Okay? So then I'm adding the statement about the extensions, if you look just at things that are valence 2, say that every single edge is paired with another edge that runs backwards. So in this case, 1 is paired with 2, 3, 0, and 3 is paired with 0, 1, And so I could think of these now just formally as two-way edges. In fact, in the sense of a train track, what I want to do is think of the tracks now as many of the tracks allow you to run both directions on them because of this pairing, this extension. Okay. Other questions? So, okay, let's go back to this picture then. This picture here, with this information, there's my 1, 2. 1, 1, and 3. And now let me just try to put back in the green arrows that express this as an extension. So there's 1, 0, so 1, 2, 3, 0. And here I should have a backwards running arrow just like I had before. So 2, 3, 0, 3, 0, 1, 2. And then something funny happens. So the point is that when you're loop type, then you're just doubling your arrows, or creating backwards paths. I guess to make that less confusing, maybe you should imagine that as running the other way. Okay. And but here the paired up arrow is actually 3, 0 over here. So why is that true? Well, I got a 1 followed by a 2, 3, 0, but I could also do 1, 2 followed by a 3. Oh boy. Three, 0, 1, 2. Oh, good. That's great. That cancels out my other mistake that was coming in 5 minutes. Okay, so is everybody happy? I mean, see, let's one more time. I could go by 1 and then take D again and multiply 1 by 2, 3, 0 to get 1, 2, 3, 0. Or I could have stayed fixed at this point, picked up a 3, 0 and followed it by a 1, 2, and that would give me that the square of this point is this point with the right thing acting on the left. Okay? So I do get U by the identity. Okay. Okay. Okay, great.
But that means that
No.
when you erase the zeros, you didn't get what you originally had.
When I erase the 0. Oh yeah, I'm very unhappy with this actually.
Isn't the idea that, like, when you say that
No.
A it has an extension, CFD has an extension, that means that if you, like, then restrict, you get back what you started with. And restricting, I assume, means
Yeah.
kill all
zero,
zeros.
kill zero. I'm deeply disappointed in myself. So why does this work? Okay. So the claim is that this is what it is. Oh, of course. Okay. It's U times the identity matrix, right? So actually, in the image of delta tilde squared on this dot, I better not see this dot. Or that has nothing to do with the identity. Do people agree with that statement? People are nodding like, oh yes, stupid, way to go, way to catch up. Okay, so the point is that this 1, 2, 3, 0 that I do see, I need to cancel that with something else, namely this 1, 2, 3, 0. Now you guys aren't going to, you stopped believing me a while ago.
Yeah, and that cancels with 3, 0, 1.
Okay. All right, well, rock on. See, I knew that I wasn't going to be able to stand there for 10 minutes. I actually had to sort that one out. All right, so what happened? So, the point is that I have all of those tracks now run both directions. Okay? And I have these two additional tracks. One is this one here. And the other one is a 3-0 that runs from here. Okay, and so you should check that this curve would pick up a row 3 corner followed by a row 0 corner. And so that's why this curve in that direction is adding exactly the one more piece of information, that row 3-0 edge. And that's the crucial thing here. Okay, so now there's some Blackboard magic that happens, and that's that it's still the case that arrows are paired up, at least in this picture. And so another way to draw this would be to write this slide the green arrows. You have to convince yourself that I'm not going to change anything about this diagram. I'm just going to draw a different version of the same picture. So all of the same information about this algebraic gadget will be encoded in this train track picture. Okay. So that's the train track I want to consider. I'm claiming that this extended object should be thought of as this train track. And now there is a linear algebra miracle over f adjoin u mod u squared that occurs, which let's say this is linear algebra. And you need to use the fact that I have this extension. So when given m, it is possible to choose this train track of m so that first of all I get some collection of immersed curves. You think of these as two-way tracks. And together with, this isn't going to work out to be a sentence, but okay. You have a collection of immersed curves that are these two-way tracks plus with some number of switches. So I checked at some point online at pictures of train tracks. These are called scissor switches, I believe. So I'll draw the red immersed curves in. So you'll have two-way tracks, and then occasionally you'll see switches that allow you to change tracks here. But you can't change from this track and move and go the other way on the other track. You can switch tracks, but you can't switch tracks and switch direction on the other track. Okay, so those are directed, and we should just give these some notation. So this is just really, I'm claiming that I should just work with immersed trivalent graphs with special edges. And the special edges have the following form. So those are the objects. Now what it's really important to just take stock here. I'm not claiming that, if I write down any collection of dots with arrows for which d squared is equal to 0, that I'll be able to do this. I need to know this extension property. So I need to know that I have this one additional property that's something about the 3 manifold. Okay? So in that case, I can work with this object instead. Okay, so let me finish going through this particular example. And other questions?
That doesn't look like what you have over there.
It doesn't look like I have here. Yeah, so I slid it this way.
Oh.
Okay, and I claim that picture and that picture, if you follow around the graph and just see what the instructions tell you, that it's describing exactly the same algebraic data. But now, when you're asking, I always feel like I should check.
Which one? Which way? Oh, you slid.
So like if I go from this horizontal piece of the track, which is that loop, I'm allowed to run off that track down onto the vertical, which hits that dot there. That's the same thing as going here as veering off that track and then up onto. It's the same information. This is just a more convenient way to draw it. Perhaps a more suggestive way. And the fact that I can do that is this linear algebra. Okay, so it's not. I'm not saying it's like supposed to be obvious by monkeying around with this example, but this is not like there's content here. But it is it's linear algebra, and I should really say that this is. Jonathan claims this is largely to do with the fact that he was teaching linear algebra last semester. So you should always.
Sorry if this is obvious or you said it, but what does rho not represent, like in the picture of a bordered Haggard surface?
It represents one of these disks that can now cover the Reeb chord rho 0, so it can cover the base point, but I'm only allowed to cover that base point once, which is why I'm working mod u squared. Okay? And I should say that this is like, I'm not making claims about what happens if I work with like the full cover rho 0 as many times as you want. I think that's part of the theory that's in development, and this is like we're sort of bootstrapping up from the bottom. But this is a trick that was used in the faithful option of the mapping class group paper when they were working out the bimodules for arc slides. There was this trick of expanding curves to either side to get a little bit more control on what curves could show up, what operations could show up. Okay, so this is not like fully out of nowhere. It's definitely heavily inspired by what's going on in the literature leading up to this. All right, well, there we go. So let me now just finish by drawing a suggestive collection of pictures. So what you do, so now what you do is you try to manipulate the picture into something you can deal with while carefully not changing the box tensor product as you go. Because you want at the end to be able to say that, oh, well, the pairing is still the pairing I expect. And I'm not going to be able to say all of that, but let me just finish with a cartoon. The cartoon is this. So here's an exercise. Again, it's not dissimilar to the exercise that Adam and I just did together here. Here's the track that I started with. Let me get the arrow the right direction. These describe exactly the same type D structures. Like this is not a change of basis or anything. These are just two different descriptions of exactly the same curve information. Okay, so that's fun. That's just counting tracks. Okay, nobody believes me because I've made like there's some bound on the number of errors you can make. But okay, and then there's some tricks you can do, and you should write down. So I'm gonna write down exactly what the claim is that I'm starting with this picture. And then I'm going to try and get myself to something simpler. And that's this. So I can remove, the claim is that I can remove this one arrow by a change of basis. and then I can remove this arrow. I change the base. So I can do this all in one. And okay, so there's explicit changes of bases that give me homotopy equivalences of the type D structure. And so at this step, I get this picture. So if this is, I'll tell you what they are so that you can. And then I'm going to switch to a B prime, which is going to be A plus B, and write this now as A 1, 2, 3. Okay. So, okay, at least in this little toy model, what is this claiming? This is claiming that, so I have some matrix that encodes the type D structure. I have some matrix that encodes the extended type D structure, and I can conjugate a similarity class that doesn't change this information at all and just has, well, what's really happening, these arrows are running clockwise around the box. And then there's a series of moves that when I see a curve diverging, there's a change of basis that I can use to get rid of that curve. And that's the same thing that happened here. There was a change of basis that allowed me to switch this curve to the other side of the torus. That's something non-trivial in terms of homotopy. And I can remove that curve by pushing it through by another change of basis in the extended type D structure. So these are supposed to be on the right, so I should. This is some explicit changes that take me from this naive, non-loop type looking object and display that, oh, it's actually loop type. And these pictures are supposed to encode some series of linear algebra that allows me to actually change the train track slowly into an immersed curve. So now I've gone over time. What I'm not claiming is that you can do this all the time, and that maybe by staring at what's going on here, if you believe me that the change of bases are happening when curves diverge, precisely when this won't work is when you have a pair of tracks that run parallel around the torus and come back to themselves. Those are exactly the curves that I can't remove the switches from. But that's okay. What you can do is you can collapse all of those parallel running curves together, keep track of that with a vector space of dimension number of those curves, and then use the arrows to encode a local system. So I'll stop, but that's the story. Okay, thanks.
So what's the algebraic takeaway from what about what you can do when you don't have loop type? I mean, what should I have in mind?
Right. So
you
this.
have to work over this extended algebra.
Yeah. So
And what else?
you should work. No, you still work over the extended algebra allows you to do the linear algebra to make the following statement. And the following statement is that now I'm allowed to consider everything to be loop type, modulo having local systems decorating those loops. And the local systems tell me the dimension of the vector space, tells me how many parallel running curves I have, and the endomorphism of that vector space tell me just they encode exactly the arrows that are these switches that are running between those tracks. And so now the statement, you go back and you say, oh, you just soup up the Lagrangian intersection floor homology statement with intersection floor homology with local systems, and you're okay. And then you go back to wondering to yourself, well, can I even produce a 3-manifold that has a local system? But at the end of the day, so somehow spending time on the immersed curves that's the point. That tells you, this quantitative data about how L spaces are behaving. But then more generally, why is that working? And it's because a linear algebra miracle happens. Sort of. Does that help?
Yeah.
Yep.
You have local systems over what?
They're just the two-element field. Like they're just the vector spaces. Everything is mod 2 because I'm working over. Because we're working with bordered, and so the notice what's happening here is I'm considering these two-way arrows. That's just being governed by the extensions. But the extensions aren't telling me anything about the border invariance. They're not telling me anything about the hat invariance. So for the hat invariance, I'm just working mod 2. And the local systems are just, they're just vector spaces over the two-element field.
Okay, but
Plus
of any dimension.
Any dimension. And the dimension really, I mean, so we didn't talk about admissibility. So, you know, the place where the local system matters is where you've got parallel running curves that you want to intersect. But typically what happens is you're intersecting two sets of curves and they're transverse, and it's just all the local system's going to do is the dimension of the vector space is going to multiply the size of your floor homology. So you see, at least, again, quantitatively, that things only get worse as the information in your boundary has train tracky behavior. You get more intersection points, not fewer. Coffee?